V1 algorithm, there were 43. I applied my histogram test to it, left 38. And then here is the example of those numbers in the data. Between the bars is what matched, and you can see, wow, those are credit card numbers. And then before it, actually, I didn't put in this is in the database. They actually tagged it with the name of the financial institution that issued the credit card. And here's the position within the file. And this is what I call my feature file. And this feature file is very useful for doing the correlations later, but you can also just sort of look at it and make a decision. Now, here's false positives. These numbers all pass the credit card number validation algorithm. They all have prefixes that could have been issued by banks. Before and after the dashes or the vertical bars are what's in the context. And you can see it doesn't really look like it was part of a real database. Those don't really look like real credit card numbers. So these are false positives. It's not a perfect algorithm. That's okay. So I ran the scan over the 2003 corpus of 178 image files. I found 47,000 credit card numbers, of which 15,000 were distinct. And here's the most popular credit card number. I found it 34 times on 30 drives. So that's not good. Like, why would you find that? So this is clearly a false positive. And you can see even the context is, this is the drive number, drive 6, 7, 8. The context is before and after the same. And so this could easily be from like a DLL that's part of the Windows operating system, maybe. Well, we could put it on a stop list. Say, okay, if we see it on all those drives, ignore it. Take it out of the analysis. So I do that and run the numbers again. And now the most credit card number, again, it looks like that. And in fact, the context, it even looks like it has some C code after it, a printf performed. So this stop list approach, I don't think is a good approach. It's the obvious approach, but it's a pain because you have to construct this stop list. You have to maintain it. You have to tune it for different applications. It's just too much work. It's more work than I want to spend. So instead, what I just do is I hope that my credit card number detector is good. I manually tune it up. That's why the histogram test is there. It seemed like a good test. But then I just hope that the majority of the positives are going to be legitimate positives and that the false positives will be lost in the noise. And in fact, they were. So this drive here, 5,000 credit card numbers, of which 1,300 are unique. This drive here, 1,200 credit card numbers, of which 286 are unique. This one, 31,000 credit card numbers. So then, once I have these drives to look at, I can look at them with manual tools, like encase or strings or what have you. And I did that, and I found that this is that hard drive from the supermarket. This is a hard drive from a software vendor. They're selling software over the internet, collecting credit card numbers. This is from a medical center in Florida, 31,000 credit card numbers. And then elsewhere, diagnostic codes, and elsewhere, billing units within the medical center. This drive did not have a file system on it. The drive was an Oracle raw data drive. So if you had gone into that hard drive with a tool like Encase would not have been able to identify a file system, and all it would have been able to do is do string searches. And yet, that's one of the most interesting hard drives in my entire collection. So the second order analysis actually does correlations between multiple drives. It says, okay, can we find drives that have something to do with each other? And I was sitting at MIT with a friend, and I said to him, I wonder if any of our hard drives have credit card numbers in them in common with other hard drives. I wonder what that would mean. Well, so I built some technology, and I ran the study, and then I had to figure out how to visualize it. And this is the visualization. So this is the first drive, and this is the second drive. And the peaks are the number of credit card numbers that they have in common. And so all this noise down here, these are all the false matches from like the false positives. Every drive that had that thing that looked like a credit card number that made its way through. But this one here, that's 25 numbers in common. This is 13 numbers. This is 13 numbers. Let's look at them. Well, it turns out that these are from the same medical center. And what that medical center had done is that one drive is that Oracle data drive. Another drive was a drive that had a Unix file system on it, and it had source code on it, and it was their development drive. And they had taken live data from their production system and used it on their development system to do testing. And I found that automatically. Here, these are 2 drives from that same car dealership, the one I mentioned earlier. Now, the algorithm didn't know that they came from the same reseller on eBay. It found that out. Now, of course, there were other drives that I bought from the car dealership, it turns out, that did not correlate. So I'm getting lots of false negatives. I'm not finding all the correlated drives. On the other hand, I'm only doing the correlation with one thing here, credit card numbers. And I could correlate with other pieces of information. I could correlate with email addresses. I could just do the MD5 of every block and treat that as something to correlate on. And these came from the same community college. Now, I've written a paper on this, and it's in submission. And what's very interesting here is that these are actual real credit card numbers. But here on the community college and here in the dealership, they actually correlated on false positives on the credit card number detector, showing that it's not that they're credit card numbers that's important. The thing that's important is that it's what I call pseudo-unique information. It's information that you tend not to find in the wild, but if you find it in more than one place, then there's a high probability that the data actually got moved from one place to the other place. So other things that you can use, as I said, you can use message IDs. Now that's very interesting. Those are supposed to be unique per email message, so you can find out if 2 hard drives touch the same email message. Maybe because one person was sending mail to another person, or maybe because they were both on the same mailing list, or who knows. And as I said, MD5s of disk sectors. So what can you do with this? Well, you could identify social networks. You could test for inclusion in existing network. We have this drive from a suspect. Who else does that person communicate with? Or you could look for the dissemination of information. We have this PDF. Maybe it's PDF of a manual. Maybe it's like that Al-Qaeda training manual. And we can take that PDF, break it up into each block, calculate the MD5 of each block of that file, and see who had those blocks on their hard drives. Even if they deleted the file and it was partially overwritten, as long as there are some remaining blocks. An interesting fact of today's file systems is that they always block align large files. So small files might not get block aligned because of the way these high-performance file systems work, but any file larger than 4K always gets block aligned. And so the 15th or 20th sector in that file will almost always be a unique disk sector. And if we calculate the MD5 of every disk sector on the disk, we'll find it. So this is pretty cool. And I talked about that. So reactions to this research. After the first paper was published, there was legislation that was introduced in July 2003, the Fair and Accurate Credit Transactions Act. And surprise, surprise, they put a requirement in it that companies getting rid of hard drives had to be sure the consumer records were removed. And I feel responsible for that, so I'm really happy. And if you go through the congressional testimony, it does seem that a lot of the news coverage that we had in January 2003 was responsible for that being put in. Another reaction was the Secure Empty Trash feature in macOS 10.3. And I interviewed the people in Apple's security group, and they actually added the Secure Empty Trash because of the paper that was published in 2003. And that's really nice. It's nice when you can have an impact on a company with research that you do. Unfortunately, they didn't do a very good job implementing Secure Empty Trash. It's implemented inconsistently. They implemented on the Finder menu, but not on the control menu for the trash can. It's really not even clear what Secure Empty Trash means unless you're sort of up on this stuff. And once you're secure emptying trash, you can't use the trash can. It's a very slow process. It doesn't happen in the background. But the worst part about it is you can't change your mind. If you accidentally empty the trash, and then you say, oh no, I should have secure emptied trash, it's too late because the files are deleted. What the Secure Empty Trash does is it overwrites each file, and it does it at the user level. It doesn't even do it within the file system. So there may even be an interaction with the journaling file systems that the Mac uses. And I just don't know right now, but I'm doing some research on that. Now, macOS 10.4, they said, oh, well, we'll deal with that problem. It's as if they're reading my presentations and fixing their operating system. They added this button to the disk utility. It says erase free space.